All right, we'll start. So good morning. So this is the last lecture for the course. We'll talk about the last family of generative models, which are diffusion models. So we have quite a lot to cover today. So I will do a quick recap on VAEs, which we covered last time. And then I will tell you about how we can derive from VAEs diffusion models by extending the architecture, by adding several layers to the architectures of the VAE. And so this is what we'll cover in the second part about variational diffusion models. And then finally, but I will talk about that only very quickly, I will also tell you that we can revisit these variational diffusion models from another perspective, which we call score-based generative models, which I will mention, but you can skip that. So we'll do most of today's talk, today's lecture on the blackboard, so because I really want you to understand how we can arrive from the VAE to the diffusion model slowly. And so, yeah. So for once, I will start with a few applications, just to motivate why it's important and interesting to study this class of model, despite how complicated they might look, at least at first sight. So basically, VAE diffusion models, they are really now, these days, the state of the art when it comes to generative models, deep generative models. So you can use them to generate mostly any kind of data, but they've been mostly used and developed to generate images. And so they've beaten previous state-of-the-art architectures, which a few years ago was about generative adversarial networks, but we don't use them anymore because they have many problems. They are difficult to train. They are very unstable. And yeah, it was really an art to make them work. When it comes to diffusion models, it's much simpler. The training is much simpler. So what you see in the slides are a few images that you can generate with a diffusion model. And so formally, the task and you will see that diffusion models can solve many tasks that actually are very close to one another. But the first task, task one, is simply to learn, a probability distribution over data. And you parameterize this distribution with parameters with an architecture, which in this case will be a diffusion model. Okay? So this is the target, to learn this distribution when we are given a data set, I would say I from a data set of samples of data, like you have a data set of images, and from this data set, you want to produce a good model of the distribution that could have generated these images, let's say. So this is the first task, the simplest, at least in its formulation. But of course, you can extend that. You may want to generate data conditionally on something. And so this is something that I suppose you know very well. For example, the case of generating images conditionally on text, conditionally on a prompt. It's a variation of this problem where now the task would be to generate or to learn a distribution still over similar objects like images, but you would do so, for example, conditionally on text, on a prompt, or you may want, I don't know, to generate some piece of data conditionally on a style, conditionally on a class, whatever. Okay, so this is what we call conditional generation, and the architecture that we'll see today, they are very convenient because it's very easy to make them conditional, even without retraining. This is something that you can also do with a VAE. That's something that I've mentioned very quickly at the end last time. For example, if you add auxiliary inputs to the decoder of the architecture, these auxiliary inputs can correspond to this conditioning that you add, like text, style, class, or whatever. Okay, so you may ask, of course, what's the point of studying neural network that can generate images conditionally on a prompt? And I would agree with you. However, the same kind of models can be used to solve more interesting problems, and many of them can be framed as solving inverse problems, where you are given a measurement, which can be, for example, a noisy image, and what you want is to remove the artifact of, for example, the measurement device that you have. And so you see a few examples there on the slides. Let's say you get only, so you want to go from a very sparse image, so where you only get to see a few pixels, and you want to recover the entire image, or you want to do in-painting, so you only see part of the image, and you want to infer the content which is missing, or you have a blurry image because of your instrument, of your camera, and you want to remove the blur to recover a crisp image, or you have a low-resolution device, like you have low-resolution images where clearly you see the pixels and you would like to produce a higher resolution version of that image. This is the problem that we call super-resolution. You could have also different kind of blurs. So I mentioned above the Gaussian blur, but you could have also motion blur and other kinds of artifacts that are due to the to motions or other processes. So these are examples of what we call linear inverse problems, where you can define the mapping between the measurement and the target simply with a linear function. But of course, you can extend that to nonlinear mappings, where you have, for example, you only see a few of the phases, or you have non-uniform blurring effects, and many, many other things. And so in this case, the task is also very similar to the one that above. The task of solving an inverse problem is to recover a posterior distribution, over data, given some measurement y. Okay? And we assume, in this case, that we have a prior in the form of a generative model. So P of x is the prior, but it's also the diffusion model. And we have a good understanding of the relationship between x and y, okay, but in the causal direction, okay, where we understand why the measurements are distributed given some piece of data. Okay? So this is a very generic problem, and it finds many, many applications. Here you see a few of them in the case of computer vision, but also in many scientific domains. You have very similar inverse problems, and diffusion models can be a solution for them. You can also extend generative models and diffusion models specifically to other kinds of data than images. And here I've just cherry-picked a few of them, 3 of them. So you can do, so if you understand that you can generate images, then there is only one step to generate videos, which are sequences of images. And this is an example that you see above of the sketch of an architecture based on a diffusion model, which you can use to generate videos. So this would be a task 4, where you would have, you want to generate a video of which can be quite big, and also maybe conditionally on something. You can also use diffusion model to generate 3D objects or scenes. And so this is what you see there, where the goal is to generate a point cloud that would represent the shape, the geometric shape of an object, in this case, a plane. Okay, so you can use that to generate basically meshes, and then from these meshes to use them for some other task. And finally, a last example where you see them being used to generate the 3D structures of proteins. And in this case, it's something which is done also conditionally, in this case, conditionally on cryo EM images. Okay, but this is still an instance of that or that problem. Okay? So this is just to say that basically you can be as creative as you want with this diffusion model. You can apply them to many kinds of data. It does not need to be within the scope of images only. And I would say images are actually now the least interesting modality of data, but you can apply them to videos, 3D shapes, graphs, in this case molecules, but fundamentally it's just graphs. You can also apply them to generate text, even though they are not as good as what you would obtain with a regular transformer, but they are variations of diffusion models that you can also apply on text to generate text, and many, many other kinds of data. And finally, one last application. This is something we've been working on actually here in the group at Montefiore, where we have developed a diffusion model, a quite large diffusion model to model the weather. So in this case, the task was to generate states of the atmospheres at the scale of the entire planet. And so we were dealing with very big objects. So what you see there are the inputs that we want to regenerate. They are basically maps, fields of physical quantities like temperature, humidity, speed of winds. And we have a description of the atmosphere at several layers of pressure, of altitudes. And so at the end, you get an input for describing one state of the atmosphere at one specific time step, which is in the order of 200 millions of values. This is one frame, if you want. And so what we do, of course, is, in this case, we can't directly apply and learn a diffusion model on this, but we can do a trick, which is to go through latent space. So we can compress the data with an autoencoder, and this is what you see there at the top. So you see an encoder architecture that goes from these very high-dimensional maps and then compress the data, in this case preserving the 3D structure that you have because the data is located on the sphere, on the planet. And so we take that into account. We compress the data spatially to obtain a very compressed representation of these states. And then, now that we have compressed, if you want, the images of the atmospheres, we can learn a diffusion model that would produce videos of these compressed representations. Okay, and this is what you see there, and this is something that you will recognize later in other examples that I show, but you had at the middle a diffusion model, and the diffusion model is itself, in this case, a transformer, and takes as input noisy version of these states, and then from this noise is able to produce segments of trajectories, which then we can combine to produce videos. Okay? But again, this is just learning something like this, where now you would have, in the case of videos, we learn actually a prior that we can use to generate trajectories, so sequences of several frames, so from 1 to L. And then once we have this prior, because of the properties of the diffusion model, we can also condition the generation. So we can also do things like generating conditionally on, for example, observations. And so in this case, what we did was to condition, for example, on weather station measurements, so things that are very local and noisy, or to condition on satellite measurements. And at the end, in terms of results, you get something like this, where you can use your diffusion model to generate entire videos of the atmospheres, and you can do that, for example, to do weather forecasting or to do data simulations and many other tasks of this kind, which you can actually just almost always reframe as an inverse problem or a posterior inference problem of this kind. Questions? Okay, so this is just to say basically that what we are about to cover today is something which is very versatile. You can use diffusion model to solve many, many problems. And so it's a very important topic in deep learning. All right, so let's start with a short recap on VAEs, because I will then build upon VAEs to derive diffusion models. Okay. Okay, so if you remember, we define VAEs with two variables. We have the data X that we want to model, or we want to model a distribution of that data. And we have also latent variables, okay, which we use to generate the data. And so we have a relationship that goes from Z to X, and I call that the decoder. And the decoder basically is nothing else than a probability distribution over X given Z. Okay? But we have also seen that in order to train this decoder, it's not something that easy, and the trick that we use is to do variational inference, which basically is saying that we are instantiating another distribution, which would be more or less the opposite of the first one, which in this case we also call the encoder, and which gives us a mapping that goes from X to Z, and so it's conditional distribution on Z, the latent, given X. And we also instantiated this distribution as a neural network. Okay? And so in this architecture, the goal is to learn this distribution. Okay? This is only something that we need in order to train the decoder, but really the pieces which is interesting is the decoder, because this is the thing that we'll use to actually generate data. And the way we'll do that will be simply by sampling from the prior that we have, PZ. And then given some Z, then we instantiate this distribution that gives us a conditional distribution over some Z that we have drawn from the prior, and then we draw some X data. Okay, so how do we learn this model? Well, as usual, what we did was to maximize the likelihood of the data. And so in this case, we are trying to maximize the marginal likelihood of the data, so P of X, where you have the theta parameters, because I'm really considering the marginal over this joint. And what we've derived, okay, so we have expressed the marginal. So we can express the marginal as the expectation over Z of Px given Z. Okay. But then we quickly realized that if we wanted to maximize this, we needed a way to evaluate this expectation. And so we could just say naively, okay, we just do Monte Carlo. We'll do a Monte Carlo estimation of the expectation, but the variance and the quality of this estimator would be very poor, because a priori, if you just draw Z's from the prior, it's very unlikely that they would happen to explain the data very well. Okay? So in order to be more efficient, what we did instead was to consider the encoder as a way to sample Z's that would already explain the data well. So we switch the sampling distribution to the encoder. We still maximize the same quantity, so the conditional density of the data, but of course, since we are no longer sampling from the same distribution, we have to account and make a correction, which in this case was equal to the ratio between the prior and the density of the given by the encoder. Okay, and then we were stuck, but we can derive from this a lower bound on the log of the marginal density. And the lower bound in this case was equal to the expectation over Q of the logarithm. And I will write it in this form here for today, of the joint of Z and X. I'm just coupling these two together in the joint, as the joint. Over this. Okay, and this is what we call, so how did we call this expression, this objective? The elbow, yeah. Okay, and what is important also, and will be important for today, is that this is something that we need to evaluate at every x that we have in the data set. Okay, there are a few things missing there. Should be a theta, should be a phi. Okay, and this can itself be rewritten in a way which intuitively makes sense as the sum of two terms. The first is the expectation of the conditional density. So this of the log of the conditional density. Okay. Plus, or minus, sorry. Minus the KL divergence between QZ and the prior. Okay, and so in this form, what you should recognize is that if we are trying to maximize the elbow, then we are trying to maximize this expression, meaning we are trying to maximize this, which corresponds to the reconstruction error. Okay, so you just look at how well the data X from your training set is reconstructed when you sample these from the encoder. And at the same time, you are forcing, in the sense of the KL, the sampling distribution QZ given X to remain close to the prior. Questions so far? Oh. Okay. Okay, so I've just mentioned that this is a term which we need to remain close to the prior, okay? But actually tells us also the reason why just regular VAEs do not work very well. Okay, and I will show you why. So the objective is not exactly this one. it's the expectation of the elbow over the data set. Okay? So effectively, when you train a VAE, what you are maximizing is the expectation over the data distribution. So there is no theta there. Okay? It's the data distribution of the evidence lower bound evaluated at x. Okay? And we want to maximize it for every x from the distribution. Okay, so using the previous form, this is equal to the expectation of q phi zx of log okay, it's just this term minus the KL zx and the prior. Okay? Okay, so now I will look at this term. And I will call that omega. Okay, and I include the minus sign there. So we have that omega, and when I mean omega, it's omega in expectation over px. Okay, so we have that omega is equal to the expectation over px of minus this KL divergence. Okay, and the KL divergence can be itself rewritten. So it's an expectation over Q of the log of the ratio of the two. Okay? And because there is a minus, it's the same as the expectation over the first of the log of the ratio of the second over the first. Okay? Which you can itself rewrite as a difference of log densities. Q of log PZ minus log Q phi ZX. Okay, so far? Okay, so now we can look at these two terms one after the other. So I first have the expectation of the log PZ. So, and this can be written. So you see, you can couple these two things to have a joint distribution over x and z, okay, where you sample first from the data distribution and then conditionally some z from your encoder. And you see also that this term does not depend on on x. Okay, so you can marginalize out the x's. So this can be rewritten as an expectation over something that I will call q phi z, the marginal distribution, but where this guy, okay, is equal to px of q phi z x. Okay. Of log pz. Okay, so in a sense, this thing is, another name that we give to this marginal distribution of the latence is the aggregated posterior. Why? Because you just take the average of the posteriors, okay, of the conditional distribution of the latent given the data. Okay, each one of these terms is a posterior given some x, And then you just average them all to aggregate them all. Okay, and so before moving on to the next term, this is equal to, so do you recognize this from before that we have seen in previous lectures? The expectation over a distribution of the log of some other distribution. It's exactly the cross entropy, or the negative of the cross entropy, in this case, between the aggregated posterior and the prior. Okay, and so we are trying to maximize omega. We are maximizing the elbow, so we are maximizing this part, maximizing omega. And so maximizing minus the cross entropy is the same as minimizing the cross entropy. Okay, which means that will happen when the aggregated posterior is equal to the prior. Okay, so that's actually the goal. It will be for the, if you look on average over all the posterior that we produce, we will try for their marginal densities to correspond to the prior. Okay, and then we have the expectation over px of this, of the expectation of, sorry, over px of the expectation over qz given x of minus log of that same density. So this is the entropy of the posteriors in expectations. Of Q. Okay, so this H means the entropy. Okay, so not only we are trying to minimize the cross entropy of the aggregated posterior with respect to Pz, but since we are maximizing this quantity, we are maximizing this expected entropy. So at the same time, we want the posterior to be as entropic as possible, so to be as wide as possible. Okay, it's when you will have a wide posterior that the entropy will be the largest. Okay, and already there you should see that that will be quite difficult because, okay, if that's the goal, we want the entropy, the posterior to be as large as possible. This will be counterbalanced with this term, which at the same time will impose that given the posterior that we have, we want to explain as best as possible the data. But that's one easy way for this to happen is to concentrate the density of the posterior to just a very small patch of the latents, so that only these small subset of the latents are actually used to explain the data. Okay, but that will not happen, actually. It looks like it should happen from this, but because of the prior matching term, this one, that will also lead to this counter effect. Okay, so just to give you some intuition, let's say we have a two-dimensional latent space, okay? Dimension 1, dimension 2. And we have a prior over this latent space, which usually is just a Gaussian prior, okay? So in 2D, we would have a density like this, okay? Where most of the density is in the middle and then vanishes as we go further and further away from the mean of the Gaussian distribution. Okay. Now, if you look at the aggregated posterior, QZ, okay, so the expectation over px of the posteriors of the QZ given x. Well, for what, let's say you pick one x, the density will be placed somewhere in the latent space. Okay? So for example, for some x, we could have a posterior density which is concentrated there. For some other x, we will have maybe a density which will be like this. For maybe another one, we'll get something like this. And each one of those posterior will be forced, because of the reconstruction term, will be forced to be peaky. Okay? Let's say we have another one which is there. And maybe another one there. Okay. Now, if you repeat this, and then look at the average distribution that you will get something which maybe will look like this. It's as if you were doing a mixture of all these distributions. Okay? And this weird thing that I've just drawn corresponds to the aggregated posterior QZ. Okay? And intuitively, what you should understand is that we are trying to align this weird potato, because of this term, to this nice and simple Gaussian. Okay? So we want the red to match with the white. Okay? And so ideally, what we'll want, for example, in this part of the latent space, the aggregated posterior has almost too little density, so we should try to move the density closer, or to align it to the density of the prior. That's the same here. That's the same there. We want to move it in this direction. However, the aggregated posterior could also spill over outside of the prior, for example there, and in this case, we should rather try to move everything to the inside, like this. Okay? But that's something which will be very difficult if you approximate your distribution with just a bunch of Gaussian distributions. You know that the aggregation of them will remain highly multimodal at the positions of each of the posterior. It will be smoothened in between, but it will remain highly multimodal. So it will be very difficult actually for the VAEs to manage to learn something which aligns with the prior, which is just a unimodal distribution. So that's one of the reasons why VAEs do not work, is because solving this problem is quite difficult given the constraints that we have in the architecture. Okay, so how can we solve this problem? Would you have a solution? So we are trying to align the red one to the white one. Yeah. Yeah, that's the trick. Instead of trying to force the red one to align with the white one, maybe you can just relax the problem and add degrees of freedom directly at the level of the prior. We don't really care, actually, if it's Gaussian or something else. Do we? So the idea is to make this distribution a parametric distribution such that we will add parameters to it. And now we will have the extra degrees of freedom of keeping the red one as it is, and instead of trying to force it to align with the white one, to do exactly the opposite, to actually modify the prior such that it better aligns with the aggregated posterior. Okay, but that means now I need to pick a distribution, a parametric distribution for the prior. Which is what I'm trying to do, right? I'm trying to do that. Except that now I want to do that at the level of some other variable z, but mathematically it's still the same problem. So what distribution would you pick for the prior? So do we know in advance what will be a good choice for the distribution? No. Okay, so maybe we should use something which can learn a good distribution directly by itself. Haven't we seen something like this? Yes? It should be what? Yes, but the neural network would be used how? Yeah, almost. Okay, so I agree with you. We could use a neural network, but we need a neural network that can instantiate a distribution. Okay, what kinds of architectures like this have we seen so far? Normalizing flows. You could replace the prior with a normalizing flow. That would work to some extent, but we'll do something else. What else could we use? That's a valid choice, but we will still have issues. It would improve, but we could do actually something slightly better. Exactly. So what we'll do is to say, okay, this guy is itself a VAE. The prior is itself a VAE. I'm trying to build a VAE on the data. The VAE is tied to a prior, and I will say the prior of that VAE is itself a VAE. And so what we have is something like this now. We have the data X. We have the latent of the VAE. Okay, but I will say these latents, they are themselves produced by a VAE. Okay, so now I will enumerate Z and say that this is Z1, and I will add Z2, and there I will connect the two variables with the VAE architecture. So we have P1. And so now, in between Z2 and Z1, we would have P of Z1 given Z2, and here we would have Q of Z2 given Z1. Okay, fine, but what's the prior I should use for Z2? Another VAE. And you can do so many, many times, let's say T times, and you basically stack upon one another T VAEs like this. Okay, and what you obtain at the end is what we call a Markov hierarchical VAE. So you do that many, many times, and when you stop, okay, you still have the issue, but what's the prior I should use for the last one? So for this one, we'll pick something simple, like a Gaussian distribution. Okay? But now we'll have allowed for all these intermediate steps, which all together will correspond to the prior that we effectively use to generate X, to be something with much more capacity than before. Okay, so let me check where I am. Okay, so VAEs, we train by the elbow. I've just shown you that because of the prior matching term and because of these effects, the expressivity of the model is limited. And so to relax and add capacity, we have to relax the prior, which we can do so by upgrading it to another generative models. Okay, so we can do that, and we chain them, we stack them to obtain a chain of VAEs, a stack of VAEs, like this. How do we train this? So what we have, if I summarize this, so I'm defining two distributions, one that goes from ZT to ZT minus 1, ZT minus 2, and so on to Z1 and then to X in this direction. And I have the encoders below, which define the distribution using the opposite factorization. So that starts from X, then generates Z1, then Z2, then Z3, up to ZT. Okay? So what we have are two distributions, two joint distributions. The first one, the generative part, gives us a joint distribution over X and all the latent, okay, from 1 to T. So this is just a notation that I use to group all the variables. Okay, and on the other hand, we have the variational distribution, Q, which also define a joint distribution, but not a distribution over X. It will define a distribution, a conditional distribution over the latent given X. Okay? Okay. And because of this structure, what we are saying is that this joint is defined as the product of first the prior, okay, then we have all the transitions from ZT to ZT minus 1, ZT minus 2 up to Z1, okay, which we can factorize from 2 to T as P of ZT minus 1 given ZT. Okay, so this goes all together times the final transition that goes from Z1 to X. And then we have, for Q, we have the first transition from X to Z1. And then we have all the transitions up to ZT. Yes. Okay, so when I'm drawing this, it's the same as saying that I assume these factorizations for the joint generative distribution and for the joint variational distribution. How do we train this thing? What would be the loss? Anyone? So I'm giving you a data set, I'm giving you a probabilistic model. It comes with parameters. What recipe do you follow? I hope you know by now. How do you train this? You maximize the likelihood. So, for training, we would be maximizing the likelihood of the data as in a regular VAE. So we want to maximize the marginal density of X. Okay. We don't care about the Z's. We only have X's that we want to reproduce. And so in this case, the log density is equal to the log of, so it's really exactly the same as this one, except that now we don't have just one variable, Z, we have T of them, but we'll marginalize them all. P. So now I have Z from 1 to T of P of X. Okay, and then for the same reasons, you can't directly Monte Carlo estimate this. It will, because the latents that you would draw a priori would very likely poorly explain this axis. So you can do variational inference. You can instantiate this variational distribution Q, use it for sampling, then make the correction, then define a lower bound on the expression, and you arrive to the elbow. Okay, and the elbow would say that you have to maximize the expectation over the variational distribution of the joint over the log of the joint, of the ratio of the joint, so this over the variational distribution. Okay, and this is again the elbow. Okay, so if you compare the two, they are really the same. Huh? You just copy and replace all the Z's with Z's from 1 to T. Okay, so let me maybe structure this. So this was 2. If 1 was VAE, 2 is Markov hierarchical VAEs. C'est bon. Okay, so this is what you have in the slides. You can just similarly to VAEs train these hierarchical VAEs by maximizing the elbow using the variational distributions that you have defined over the latent variables, and you arrive to this objective, this one. Okay? Questions? Okay, let's take a break then, and then we'll move on to diffusion models. So we'll resume in, let's say, at 45. Fine. Okay, so we'll continue. So we have talked about VAEs. I've told you that if we consider VAEs because of the prior matching term that you see there in the elbow, this term is too hard a constraint to have good results because of this effect. When you look at how the constraints, when you look at what the constraint leads in expectation over the entire data set, it means that the aggregated posterior should match with the prior in the sense of the cross entropy. Okay, and so that's quite difficult if at the same time each individual posterior is forced to be picky in order to explain, where is it? In order to explain the data quite well. And so the trick is to relax the prior, okay, and so to upgrade the prior to something which is parametric, okay. And here what we did was to say, okay, the prior is itself a deep generative model, it's itself a VAE. Okay? And so we are stacking a second VAE on top of the first one, but the second VAE also comes with its own prior. Okay, and we'll say recursively, but well, this other prior, this hyper prior is itself a VAE. And we can repeat that for as many levels as we want, and for example, up to T levels of latent variables. Okay, we arrive to this hierarchical VAE, which we can express in this form. So we have on the one hand the generative distribution that goes from latent to data, and then we have the variational distribution that goes from data to latent. Okay, and at the end we have a model that we can train exactly in the same way as a VAE by maximizing the elbow. Okay, and we arrive to this expression. Okay, so now that we have seen this, we can move on to variational diffusion models. Okay, so this thing that we have derived will help us to derive diffusion models. There are actually several ways you can arrive to the diffusion model architecture, but I think this one is quite appropriate given the sequence of lectures. But I will mention at the end another perspective to arrive to the same model. So diffusion models, they are not quite new. The paper itself was proposed already 10 years ago, deep unsupervised learning using non-equilibrium thermodynamics. It's not explained or presented in the way I will present it today. It took time first for the community to notice this paper, so it was released when generative adversarial networks were really going crazy and everybody wanted to focus on that. And so very little attention was paid to other approaches to solve this generative problem. But it's only later on, starting from the 2020, I would say that diffusion model eventually started producing results, beating the state of the art. And then until now, they remain among the best architectures to generate data. Okay, so what are they? So one way to introduce diffusion model is just to define them as Markov hierarchical VAEs in which we make additional assumptions. Okay, so we'll restrict this architecture to something actually a bit more constrained and actually simpler. So we'll erase this part. So this is what I will call VDMs, or variational diffusion models. Okay, and usually they are when you look at any blog post or paper or talk or video about diffusion models, usually they will be introduced by showing something similar to this cartoon, where you define first a diffusion process, which is a destructive process, which would start with the data, like clean images of this cat. And at every step of the diffusion process, you would add noise to the data. Okay? So in this case, you could have 1, 2, 3, 4, 5, and 6 steps of diffusions. Okay? And at every step, what you do is that you start from the previous variable, in this case the clean image, and you produce a noisified version of that image, where you add, for example, Gaussian noise to it. And then at the next step, you take the previous variables, which in this case is already an image with noise, but you keep adding noise, and you do that repeatedly for as many steps as you have. Okay? And then what is very important is that you define this diffusion process such that at the end of the diffusion, there is no signal anymore. You have basically destroyed all the information that was present in the original data. Okay? So this is the diffusion process. And so the diffusion process itself is not something which generates. What generates is the reverse diffusion process. Okay? So it's, what if we could go backward and start from noise and manage to determine what is the noise that I should remove to arrive to the previous variable, and so on and so forth, until once you have removed all the noise from this pure noise, you recover something which looks like the data. Okay? So this is what we call the reverse denoising process, which is what actually generates the data. So how does this relate to what we've seen? Well, we can define the variational diffusion model by saying that we have a bunch of variables. We have the x0 variable which corresponds to the data, and then we have all these latents. Okay? And from there on, I will remain all the latents, so the z from 1 to t, to x from 1 to t. Okay? So we have a bunch of variables from 0 to t, such that x0 corresponds to clean data, the ones that you have to your training set, and all the ones after correspond to variables that you would obtain by following the diffusion process. Okay? And how do you define this diffusion process? Well, you define random transitions that go from one variable to the next. Okay? And you do so by defining a conditional distribution, for example, x1 given x0, and I will call this distribution Q, x2 given x1, x3 given x2, and so on, and finally qxt given xt minus 1. Okay, one thing that I've not mentioned, but which is actually quite important, is that the dimension of all these variables are the same. Okay, so if x0 corresponds to for example, to vectors or images, whatever, of dimension d, okay, all these other variables, they are also of dimension d. Okay, which is something which was not necessary there. When you have a VAE and you say you stack VAEs, usually you don't say that the dimension of the latent space is the same as the dimension of the pixel space or the data space. Okay? So that's the first constraint. We say that all the variables, or basically the latent dimension, is the same as the data dimension. Okay? What is Q? Okay, these are these random transitions. In a diffusion model, in a classical diffusion model, we'll say that all these transitions, actually, they don't come with parameters that we'll have to learn. So this is why I've, in this case, actually correctly omitted the phi. Okay, there will be normal distributions with fixed parameters that I will determine before training the model. Okay, so I will have to define a mean and a variance. Okay, so that's for the diffusion part, and then we have the reverse denoising process, which goes from latent or from noisy version of the data xt to xt minus 1. Okay, so here we would have p now with a parameter that goes from that produce x0 given x1. Here we would have p of x1 given x2, and so on. And here we would have so just there we would have p of xt minus 1 given xt. And finally, we would also have a prior that comes with xt, which would be p of xt. Okay, so far for everyone? Okay, so one other way to say that is to say that in order to generate data, this is what you see there in the slides, or to, sorry, not to generate data, but to encode the data, to diffuse it and destroy it, we define these random transitions, and we say that each of them is a Gaussian transition. Okay, and the way we will parameterize that effectively will be by saying that, okay, at every step, we'll draw some epsilon from a Gaussian distribution of zero mean and unit variance. Okay, and we'll say that the next version, the next iterate of the variable, so xt, is equal to its previous version, xt minus 1, but rescaled by a factor that I need to define, which in this case corresponds to the square root of some alpha t, where alpha t will be an hyperparameter that I will define in just a few seconds, plus this random noise that I've rescaled also to define the variance that I want to apply to the that I want to have for that transition. In this case, the standard deviation would be square root of 1 minus alpha t. Okay? So that's exactly the same as saying that q of t given xt minus 1 follows a Gaussian distribution describing the distribution of xt given a mean parameter which is centered, so where the Gaussian is centered at this value, so the square root of alpha t times xt minus 1, and where the covariance matrix is equal to 1 minus alpha t times the identity. Okay? And once I've defined each one of those individual transitions, okay, if I want to define this joint, I can just multiply together all these transitions because I'm also making this Markovian assumption. Okay? So the joint of the joint distribution or the joint variational distribution over the variables from 1 to t given the actual data x0 is expressed as the product of all these Gaussian transitions. Okay, so what is alpha t? So alpha t will be a parameter that we will use to define how much we want to remove the signal from the data and to what we want to arrive at the end of the diffusion process. And so typically, we'll have that when you look at the mean parameter will be steered towards 0 as we progress in the diffusion. Okay, so we'll schedule the alpha t's or the square root of alpha t's such that it starts with some quantity, usually close to 1, and then as t goes from 1 to big T, the alpha t's will converge to 0. Okay? And in this way, what will happen is that if we look at the marginal distribution of the final step, because we have steered all the images towards 0 at every step, this final marginal distribution over xt should be centered at 0. Okay? And conversely, for the variance, you will see that we'll have a scheduling which at the beginning of the diffusion will add just a tiny amount of noise. And then so meaning that the variance of the noise will be small, meaning that the standard deviation there will be small. And so if alpha t starts with value close to 1 initially, then 1 minus alpha t is close to 0 initially. So the variance is close to 0. So we are not adding lots of noise at the beginning. But as we move towards the diffusion process, the alpha t will shrink to 0. So 1 minus alpha t will converge to a quantity close to 1. And now we'll be adding more and more noise. Okay? So the destruction process will be larger, I would say, at the end of the diffusion than at the beginning. Okay? Questions on this? Okay, what is convenient is that, of course, if we say that all these transitions are Gaussians, then there are a few properties that we can look at. So, or maybe first, let me also discuss about this figure. So there you see 3 trajectories of a diffusion process initialized at 3 different locations. So at the very top, you see 3 values, 3x, okay, in gray, green, and orange. Okay, these are just the initial value x0. And then as you go down the figure, it goes down realizations of the latents. Here they are named with z's, but they correspond to our x's from 1 to t, or in this case from 1 to 100. And what you see, the 3 curves correspond to the 3 realizations of all these variables together. Okay? And so if we say that the transitions are Gaussians, if you look at the first plot on the right, basically we'll be saying that Q of Z1 given X is also a Gaussian distribution. It's more or less centered at the initial value, but you see that it's not exactly centered. If you pay attention, there you see that the Gaussian distribution is slightly shifted to the right of the X, if we want to go towards 0. And on the other hand, for this one, the Gaussian distribution is slightly shifted to the left of this X value because we also want to go towards 0. Okay? And so you have all these Gaussian distributions that are defined at every step. This is for the very first step. This is for the steps relating Z41 to Z40 or X41 to X40. And here you see the transitions at step 80. Okay? And you see that at the beginning they may be quite further away, but if we schedule the diffusion process as we want, eventually all these diffusions will merge together. All these distributions will merge together. Okay, if everything is Gaussian, we can also define what we call the Gaussian kernel, which is just a way to say that actually, if I know that all of these transitions are Gaussian, I can go in one step from x0 to any t. And so I can go, for example, from x0 to x3. And if you chain Gaussian transitions, you obtain a Gaussian distributions over all these intermediate variables. Okay, so you have a joint Gaussian, and if you take the marginal of a Gaussian distribution, you remain with a Gaussian distribution. So if you marginalize out all these intermediate variables, you know that the conditional distribution of for example, x3 given x0 is also a Gaussian distribution, and you can derive this analytically. And so in this case, it's what you have there in the slides. If we define alpha t bar as the product of all the alphas from 1 to t, then the diffusion kernel, so q of xt given x0, is itself a Gaussian. Okay, it follows a Gaussian distribution describing the density of xt, and the mean of this Gaussian distribution is square root of alpha t bar times x0, and the variance is equal to 1 minus alpha t bar times the identity. Okay, so this is very convenient because we don't have to simulate the diffusion process if we make these Gaussian assumptions. Yes?
I have a question on the previous slide.
Yes.
On the B graph, I do not understand the x-axis. What does it represent? So, for example, we have Z1, Z41, Z81. I do not understand that. Corresponds to.
So if you take the first one, the x-axis is z1. And the y-axis is the density of that z1. And you do that conditionally on x. If you take this one, this x-axis corresponds to some value at the next transition. So in this case, z or x81. Okay. And the y-axis corresponds to the density that you associate to each of those values. And you do that, of course, conditionally on a starting value, which in this case are represented by the vertical lines, the z80s. Does that make sense?
Yes. Thank you.
Okay, so let me just... Okay, so we've defined the diffusion process, we've defined the diffusion kernel. From the diffusion kernel, we can have a direct access to the conditional distribution of any intermediate variable given the initial condition. And so in this case, what you see in this figure, if we start at x star at the very top, and you look at, okay, what are the variables this x star could reach when you just let the diffusion process run, okay, it will be defined here by this kind of cone or beam where the beam is filled by possible trajectories that could be taken by just following this diffusion process. Okay? And what is nice is that, okay, this is available analytically. We don't have to train or do anything. We just use the properties of the Gaussian. And what you see there are the conditional distribution that we know just analytically. And you see they are Gaussians because we know they are Gaussians. But what is important to see is that also these Gaussian distributions, they start with a variance which is smallish, and then as the diffusion progresses, so as you go down, the variance will increase. Also, the position of the Gaussian will tend towards 0. Okay? So this is for the conditional distributions, but what we really care about are the marginals without the conditioning. So if we were to draw all these cones for all possible x's from the data distribution, okay, and we look at the distribution, we arrive to the marginal distribution of the latent. Okay, so at the very top, you have the distribution of the data, which is also shown there in 1D. So we could have a first mode around -3 with density, and we may have x's on this part of the domain. And then we have another mode, which is also multimodal itself. Okay, but if we look, so now if we draw randomly these x's from this distribution and then compute the conditional of q of zt given these x's, and then average all over all possible x's, we arrive to some distribution, marginal distributions, which these ones, they are not Gaussians. Okay, the conditionals are Gaussians, but the marginals are not. Okay, but eventually, if we configure the diffusion process correctly, what we want and what will happen usually is that the distribution that we arrive to, the marginal distribution that we arrive to at the end, is a Gaussian distribution of zero mean and unit variance, meaning that we've destroyed completely the signal that we had at the beginning. Okay, so to summarize what we have for the so far. So if I take these guys, the encoder, I've defined q of xt plus 1. Let me just q of xt given xt minus 1. And I've said that this is a Gaussian transition producing values over xt parameterized by square root of alpha t xt minus 1, right? And variance equal to 1 minus alpha t times the identity. Okay? And what follows from that is that the conditional of xt given x0, okay, so this big jump, I know it for any t, okay, and is given also by a normal distribution over xt of square root of alpha t bar times x0 and 1 minus alpha t bar times the identity. Okay? Where the alpha t bar is just the product of all the alpha t's from 1 to t. Okay, and yeah. So we've defined, for now, just the variational distribution. Okay, and you see there that there is no neural network, right? It's just a bunch of Gaussian distributions. And these distributions, they don't even come with parameters that we'll have to learn. These alpha t's are the only thing that we have to set, but they will be set a priori. Okay? And so what was done a few years ago was to say, for example, that we really stack many, many VAEs on top of one another by saying that we have up to, let's say, a big T equal to 1,000. So we have many of these transitions. And then we have, for example, a simple linear schedule for the alpha t's that would go from alpha t equal to 1 for t equal to 0. And then as we move on, then this alpha t linearly decrease up to 0 at the very end when we reach t equal 1,000, for example. Okay? Okay, now what about the generative part, the decoder? Because we want to generate data, that's the point. So for the prior, we'll say that this is a Gaussian distribution. And it's a distribution without any alpha. It's centered at 0 with unit variance. Okay? And now we have all the steps there. So for the, let's take this one. So that will correspond to the decoder. Okay, so for the decoder, we will define P, so the conditional distribution that starts at xt, and gives us access to the distribution just before having added the noise. So xt minus 1. And we'll define this as a Gaussian distribution over xt minus 1. But we don't know the mean, we'll have to learn it, and we don't know the variance or the covariance, we'll have to learn it. Okay? So we'll just say that the mean is some function of xt, and this mean is a function that we will have to learn, so it's a parametric model, and this is where we'll put a neural network. And then we have the variance. In this case, we'll assume that it's fixed. It's not something that we have to learn, okay, and which will set to something which is predetermined. So we know we will also schedule this, the alpha t, the sigma t, the variance, depending on how we have configured the alpha t. Yeah. So now that we have that, so assuming that we know that, okay, we can use it to generate data. And how should we do that? We sample a final xt, which is just pure noise. And then we move backward from big T equal, let's say, 1000 back to 0 by following all these transitions, where at every step, these distributions tell us how we should remove the noise to produce something which will try to align with the data distribution. Okay, so there you have the reverse denoising process, spelled fully, but it's the same story, except that now you see that we go backward from noise to data. We define the joint as using the factorization, which is the same as for the hierarchical VAE. We define xt, the distribution of xt, with a normal distribution, and then all the transitions by normal distributions as well, for which we'll have to determine the mean and the covariance. Okay, so there you see that in the slide it's still dependent on xt and t, but we'll drop that when we move on. Okay. So that means to generate data with the diffusion model, at least if you follow this, it can be quite expensive, because you would need to go over all these transitions that you have defined. Let's say you define 1000 levels of latent variables, you will have to go over 1000 transitions. And at every transition, you will have to do some computation which will involve a neural network. Okay? Because of course the Gaussian distribution from which you have to sample to remove the noise will change at every step. How do we train this? Yeah. And so what will we arrive to? So we'll arrive to exactly this. So we'll have a data set over axis, which will correspond to x zeros. Then we'll not have these, but we'll have x's. Then we'll have x0s given the x from 1 to t, and we can do the same thing, define the variational distribution, which in this case is given by the choices that we have made. X. Okay. And here what we can also do in addition is to remove these parameters, the phi, because the variational distribution is already specified. There is nothing to learn for it. Okay, so it's a bit weird in this sense because we are forcing the sampling distribution, the variational distribution, to something which looks very simple, it's just a bunch of Gaussian transitions. Okay, the only thing that we learn now is the generative process itself, so how to go from the last latent to the data. Okay, so let me rewrite it maybe. Okay, I forgot that too. X0, X0, X0. Yeah. Okay, so we still have this elbow objective. Okay, so now I hope that you are ready. Okay, can we simplify this? The answer is yes. We can use the factorizations that you assume, similar to these ones, to make a lot of simplification. That's what I will do step by step with you, and you will see that we arrive to something which is so simple. Okay, so let's rewrite when I make the equal, it's the equal with respect to the elbow, not of the log density. Okay, so it's equal to the expectation over q x1 to t x0. Okay, it's the same term. And then I have the log of these two things, which I will rewrite given the structure that you assume, given the factorization that you assume. So we have first P of xt times the product of all the transitions from t equal 1 to t of P theta xt minus 1 given xt. And below, this can be written as the product of transitions going from t equal 1 to t of q xt given xt minus 1. It's also why I've renamed all the z's to x's, such that I can do this kind of tricks to simplify the notations. Okay, now let me rewrite this further. Q on t x0 of log. So I will pull apart the very last transition for the generative part, and I will also pull apart the first transition for the variational part. So we have p of xt, that's the same. Then I will pull out P of x1, no, P of x0 given x1 times everything that remains. So t equal 2 to t of P of xt minus 1 given xt. And here I will do something similar. Well, I will pull out q of x1 given x0 times t the product, sorry, of t equals to t of the transitions. Q xt given xt minus 1. Okay, so far? Okay, so this guy you agree that it's equal to q of xt given xt minus 1, but also given x0. Okay, I could introduce this additional variable. Since we know we've made Markovian assumptions, if we know xt minus 1, adding this other variable doesn't change anything. Okay? But I'm doing that because then I will call Bayes theorem and rewrite it such that I can flip the two variables. And why I'm doing that? Because if I can flip the two variables, now when I compare these conditional distributions with the one above, they will be about the same variables, the xt minus 1. Okay, so we have that this is equal to q xt minus 1 given xt x0, that's the likelihood, times the prior, q of xt given x0, over q of xt minus 1 given x0. Okay, so far? Okay, now if you look at this and you replicate this expression over the expansion of this product, this term, the xt over x0 and the xt minus 1 over x0 will simplify. Okay, if you take t equal, when you will look at all these replicates of this expression, you will have many common terms. Okay, and so a lot of things will simplify except for the last and the first term of that product. Okay, so this term I will be able to cancel them almost. We'll continue there. Okay, so this is equal to the expectation over the variable given 0 of. Okay, so I will first pull out these three terms together. Log of p of xt, p of x0 given x1, and p and q of x1 given x0. Okay. Plus so now we'll have this term, this p of xt minus 1 over, sorry, p of xt minus 1 given xt over q of xt given xt minus 1, which I will rewrite as this, okay, where in the product all these terms, they will cancel, except for the last and the first, and we'll have the ratio of this p over this q. So if we do that, we have the terms that do not cancel, q of x1 given x0 over q of xt given x0 plus the log of the product from t equal to t of the ratio of p of xt xt minus 1, yes, even xt of what remains, which will be q of xt minus 1 even xt and x0. Okay, so if you combine the two logs, we have a product, and so these two guys, they can cancel each other. And okay, we'll rewrite this further as, and you should start recognizing things that we have derived before. So I can keep this one first. Log of p of x0. If I forget some of them, for all the p's there should be thetas, except for p of xt, which does not come with parameters. So there is one missing. X0 even x1. Okay, so I've just pulled out this one, and now I have this term. Okay, and this is something that we have already seen. This is the reconstruction error. Okay, if you marginalize out everything beyond step 1, so from 2 to t, you just get the marginal distribution over. You have the q of x1 given x0, so q of z given x, of log of p of x given z. That's the VAE part, that's the reconstruction error. Plus, alors, this one is taken care of. We have this over this. Of over q xt given x0. What is this? Exactly, it's the Kehl divergence between the variational distribution and the prior. Exactly as we had in the VAE. But we have this bunch of other things too. So we have the expectation of a log of a product, which so the log of the product can be rewritten as the sum of the logs. And now we have the expectation of a sum, which can be rewritten as a sum of expectations. Okay, so now this can be rewritten as t equal to t of p, the expectation over 1 to t x0 of what? Of the log of the ratio Okay. Yeah, if we first look at this, yeah, let's say this one. This one is quite convenient because you see there is no parameter. There is no neural network. There is nothing. There is just a bunch of Gaussians. This is a big Gaussian distribution. And the marginal over the xt, the last one given x0, is our diffusion kernel, which we've derived, and I've told you this is also a Gaussian distribution. It was this one. Okay, so this distribution is Gaussian. Then we have a log of a Gaussian distribution by construction. We have said that, okay, we impose this guy to be a Gaussian distribution. And this is also the diffusion kernel, which is Gaussian too. Okay, so this one can be derived analytically. It's the KL divergence of two Gaussian distributions, which we can also derive analytically. Okay. Now, if I look at this term, so let's look at this one. And I will only rewrite this one. Okay, so you see that we are sampling the entire set of variables from 1 to t, even though we don't use them all. Okay, inside the expectation, we only require t and t minus 1. x0 is given. Okay, it's a condition. So I can rewrite this as the expectation over q, where I only query xt and xt minus 1 instead of the entire set from 1 to t, given x0 of the log of these two same things. Okay. Okay. So, if we summarize, we arrive to this, where I've told you that this is the reconstruction term. This is equal this one to minus the KL between Q of xt, even x0 and the prior xt. Okay, and this one, let's go back to it, can be further written so we still have this sum. So we can explode this joint over xt and xt minus 1 as a double expectation over q of xt and then over q of xt minus 1 given that xt, always given x0. So if we take the first one, we have q of xt given x0. And then we are left with the expectation over... Okay, let me maybe write it and not jump too many steps. Q of xt minus 1 given xt given x0 of log of these things okay, and you should recognize that this thing now is also a KL divergence term between this and that. So this is itself. Of oh, yeah, so one thing that you should add now a minus. KL between Q of xt minus 1 given xt x0 and P of xt minus 1 xt. Okay, so far? Yes.
Why the last term is not the log of the probability distribution on theta parameter? Before we had the theta parameter and we...
For the p's, you should put thetas everywhere, except for the prior, this one. Yeah, sorry. Okay, so let's think for a moment about this KL penalty. Okay, so if we just focus on variables xt and xt minus 1, we have some xt, and it's tied to xt minus 1. Okay, in two ways. First, we have the diffusion transition, so the Gaussian noise that we add to it, which is defined through Q of xt given xt minus 1. Okay. And we have the other one that goes backward and which is defined by p theta of xt minus 1 given xt. But we also have this guy, Q of xt minus 1 given xt and x0. Okay? We don't know that, we don't have it yet, this one. We have only defined the variational distribution, the diffusion process, in the direction of t going from 0 to something bigger. But here you see that it's the opposite. We have a distribution over a t minus 1, which happens before the t of the conditioning. Okay? It's because there we are defining this other transition in red, which corresponds to the conditional distribution of xt minus 1 given xt and x0. Okay? And that's this one, okay, the one that I've just drawn in red, that we are trying to align with this one, or vice versa. Okay, so what is this thing? What is Q of xt minus 1 given xt and x0? Q of xt minus 1 given xt and x0. So I've just said that we don't know this conditional distribution because we have defined the Q's in the forward direction. So maybe we can re-express this in terms of the components that we know if we could flip these two variables. Okay, and we know we can do that using Bayes' theorem. Okay, so I'm just reusing or reversing the step that I did before. And so, using Bayes' theorem, we have that this is equal to Q of xt given xt minus 1 and x0 times the prior Q of xt minus 1 given x0 over the evidence, which in this case is Q of xt given x0. So this is quite convenient because this prior is just one instance of the diffusion kernel, which we know to be Gaussian. This guy is also, it's actually the next instance of the diffusion kernel for the next time step, which is also Gaussian. And then we have this forward transition from t minus 1 to t, which we know actually does not depend on x0. So that means this guy is also Gaussian. So everything is Gaussian, meaning that this posterior distribution is also Gaussian. And so if we derive everything, we arrive to a Gaussian distribution over xt minus 1. I'm directly specifying this posterior distribution, where we'll have for the mean alpha t times 1 minus alpha t minus 1 bar times xt plus alpha bar t minus 1 square root of that times 1 minus alpha t times x0. That's for the mean. And then for the variance, we will have 1 minus alpha t times 1 minus alpha bar t minus 1 over 1 minus alpha bar t and multiplied by the identity. Okay, so this is something that I will call the mean of Q, mu Q, which depends on x0 and xt. Okay, and this is something that I will define as sigma t squared. Okay, so what's the consequence of this? It means we are trying to minimize the KL between this distribution and this distribution. We know that p of xt minus 1 given xt is a Gaussian distribution. That's the choice that we have made there. And I've just shown you that this guy is also a Gaussian distribution. Okay, it's given by this ugly expression. But it's still a Gaussian distribution. So now we are left with the fact that we want to minimize the KL between two Gaussian distributions. That's nice because we have a direct access to the analytical expression of the KL divergence in this case. And intuitively, it's super easy. If you want two Gaussian distributions to be the same in the sense of the KL, what do? You make sure they have the same variance and the same mean. Right? As simple as that. So let's start with the variance because that's the simplest. I've said that, okay, we define the diffusion process using these alpha t's, and we arrive to this expression, okay, which I said I will rename to sigma t squared. Okay, so now I will just cheat and say that when I define the decoder, these Gaussian transitions, they have that variance. Okay, so this sigma t's there, they are the same as these ones. Okay, so the sigma t's, they follow from the diffusion schedule which you define through the alphas. Okay, so basically you don't have to do anything. You define the sigma t's, everything follows for the variance of the Gaussian generative transitions. These ones. Okay, so now the only thing that we are left with is to align the mean of that distribution with the mean of that distribution. Okay, for the variance, it's just immediate, and there is nothing to be done. Okay, so we'll do that there. We are almost there. So, to summarize, we want to minimize the KL between, so what I have there, between Q xt minus 1 given xt and x0 with respect to P of xt minus 1 and xt. Okay? So, we have that this KL is a KL between two Gaussian distributions over the xt minus 1s. One with a mean which I will call mu q, the ones that I've defined there, xt, x0, and a variance equal to sigma square t, okay, and the second, or rather, the second Gaussian is also a distribution over xt minus 1, of course, with a mean, okay, which is the mean, this one. Okay, the one I've said would be produced by a neural network. And this one only depends on xt. Does not see x0. Okay. So now you can look up the KL divergence for two Gaussian distributions. A bunch of stuff will simplify because these Gaussians, they already share the same variance. And what you will arrive to is that this is the same as minimizing 1 over 2 sigma square t of the L2 norm of the two means, of the different, sorry, the L2 norm of the difference of the two means. Pum, pum, pum. Like this. Or the square of the norm, rather. Okay, so I've told you that we will impose this to be a neural network, but not yet actually, because we know a lot about UQ. We know, so our goal, so MuQ is fixed, okay, it follows from this, okay, but we know a lot about its structure. We have this decomposition in terms of xt and x0 together with scaling factors. So instead of having a neural network that will directly try to reproduce this entire thing, we could just maybe have a neural network that tries to guess the components that are missing from this expression if the only thing that we have access to are xt's. Okay, which is the case there. The only thing that enters this mean is xt. We don't get x0. So what we'll say, since we know this, we will parameterize, and this is the choice that we make, we'll parameterize mu theta of xt by following this template and then guessing what we don't know if we don't know x0. So this will be equal to wait, I think there is okay, there is one mistake, sorry, but nobody saw it. It should be divided by 1 minus alpha bar t. Now it makes sense. So we have this, and we'll say, okay, that this mu of xt is equal to alpha t. So I'm just copying what you have there. 1 minus alpha bar t minus 1 xt. So xt is known because that's an input of the function. Plus, and you will have a big plus what? Plus square root of alpha t minus 1 minus alpha t. Okay, and now we don't, okay, if we knew x0, we would be done, we would have the same mean. But we don't have that, that's not an input of the function. So what we'll do is to approximate, we'll say that we define a function which approximates x0 given xt. And this will be the neural network. We'll define a neural network that takes as input a noisy version of the data, one at the intermediate step, xt, and try to guess the clean version of that xt. Because if it can make a good guess, this would be equal to x0, and the two means would be equal, the KL divergence would be equal to 0, and the distributions would match. Okay? All right. And from this, the consequence would be that minimizing the initial KL would be the same as minimizing, still with respect to theta. And I will spare you the derivation, but you will have something which is, and it should be argmin everywhere, sorry. I should have an argmin also above. Of some scaling factors, which we don't really care about, but I will add anyway, of alpha bar t minus 1, 1 minus alpha t squared, like this, over 1 minus alpha t bar squared. Okay, so these are just scaling factors that follow from all the assumptions that we've made. Everything is known. There is nothing to really worry about. And then we have the squared L2 norm of the difference between our guess x hat given xt and the actual target x0. Okay, so this result is super important. This one. Because these terms are what contribute to the bulk of that big thing, this big objective. These are all these terms that you have there in the sums. Each of them in the sum is one of those. Okay, and basically to train your diffusion model, what you will do is to train a neural network, x hat, that will take as input a noisy image, a noisy data, a noisy version of the data, xt, and will try to predict directly as output the clean version of the data. And you do so simply in the sense of minimizing a squared error. Okay? So we've reduced the problem of generating data to just doing regression on pixels and minimizing a boring squared error. Okay, so let me just recap and then we'll take a break. I started from the regular elbow, which we can rewrite in terms of these three things. Do you see it? Yes. The reconstruction term, okay. Then at the end there, you see there, you have the prior matching term, and in the middle you have all these intermediate, these terms, which are the ones that we have just simplified. Okay. You have all the derivations in the slides to arrive to this interpretation. So we know that we have minimized the KL between these two Gaussian distributions. So given that the covariances are already aligned, we only have to align the means. The trick is to say that the mean is parameterized following the template of the mean that we are targeting. And then given these two means, these two expressions for the means, everything then eventually simplified to the minimization of the squared error of the guess of a neural network given a noisy image of the clean image or the clean data. Okay? So if we take back this, if you manage to train a neural network, let's say that would take as input x4 and would directly be able to produce x0, and you are able to do so sufficiently well for any step from 1 to t, then you are done. Okay, you have trained your generative model. Okay, so this is the first interpretation, the denoising interpretation, which is just to say you just have to train a neural network that predicts the original ground truth, x0, given a noisy version of that data. Okay? What I've not done there, but is correctly done in the slide, is that also the neural network, not only takes the noisy data as input, but of course the time step, the t position itself. Okay? If you don't tell the network at which step of the diffusion you are, then it's slightly more complicated. Okay, so we have to do that over all time steps. In practice, what we'll do when we train effectively the model is just to randomize also the choice of the time step. So at every, let's say, for every sample of your mini batch, you will sample some intermediate step t, and then you will only minimize the KL term for this time step. Okay, and because you will randomize over the t's, let's say you assume a uniform distribution from 2 to big T, then eventually you will have covered all these instances of the problem, and you will be good. Questions? Yeah.
I'm not sure I understand why we're picking like a random step in between and not just trying to learn from the last T.
Because then you are back to a VAE. If you do as if there was nothing between xt and x0, last t and x0, then it's as if you had you had not used these intermittent states.
Yes, but then the encoding of that last xt could still be more, let's say, rich in a way because of all the transformation that led to that one.
At the very end, there is no more signal. Because of the diffusion process is destructive, we don't have any information at the end of the chain. Okay, let's take a break then, and we resume in 10 minutes at 11:20. Shall we continue? Okay, so we have just derived that if you want to train a diffusion model, then if you just maximize the elbow, eventually everything can be simplified, given the choices that we made about everything being Gaussian distribution, simplify to a regression problem in which what we have to do is to instantiate a neural network X at, depending on parameters theta, that we take as input two things, a noisy piece of data together with the corresponding time step t, and then we'll try to predict directly as output, so at its output layer, the clean version of that piece of data. Okay, and you do so in the sense of minimizing the squared error between the predictions and the ground truth. Okay? So you have all these terms which are just squared errors. Then you go back to this loss, which is the loss that we started with. You have this last term, which is the KL penalty between which is a prior matching term penalty. In this case, since everything is Gaussian and does not depend on neural network parameters, we can just remove it. It does not depend on theta. Yeah, actually, this theta should be removed. Yeah, no, it should be removed. And you have this one, which in practice you can also neglect. Why? Because if we instantiate the noise schedule, the alphas, such that the noise initially is small, if because of the next transitions we solve, let's say, the problem of matching Q of x1 given x2 with p of x1 given x2. This is almost the same. There was just one transition, one small transition between that and x0 to x1. Okay? And so you can also remove this term for this reason. Okay, so that was for the first interpretation. There are actually two more interpretations. I will not develop everything as I did for the first one, but the second one is quite easy to understand. It's what we call the noise prediction interpretation, which starts from the fact that, okay, given this kernel, if we wanted to sample from this Gaussian distribution, the way we would be doing that would be by saying that xt is equal to the mean, so the square root of alpha t bar times x0, plus some epsilon noise that we scale by the standard deviation. Okay, so the square root of that variance. Okay, where epsilon is just sampled from a standard normal distribution. Okay, so you can shuffle the terms around and say that, well, then x0 can be re-expressed as xt minus this over the square root. Okay, so it's xt minus over. Okay, is that correct? Yes. And so now we have another expression for x0. We can just start from the same problem as before. Where is it? There. That this is the mean that we want to target. Before we expressed it as a guess on x0, but you could say that you reparameterize x0 in terms of the noise, epsilon, and so you copy and replace this x0 there with this expression. And again, everything will simplify, and the thing that we'll have to guess is the noise that we've added to xt. And so what we'll have instead is a neural network that takes as input some xt, and then try to guess the noise which was added to that input. And if we did that, we would recover the initial x0. Okay, so we are not trying directly to produce the data, we are just trying to predict the noise. Okay, so it's as if at every step now, you would know how to reverse a diffusion process where at every step you just add random noise. Which might be a bit surprising, the fact that we can actually do that. We can train a neural network which is actually able to guess noise, which was added to the data. And why are we able to do that? Because, of course, we trained that on some prior distribution. Okay. But if we do reparameterize, we'll have this objective function instead, where you see that we still have a regression problem in the sense of the squared error, except that now we define the regression at the level of the noise, the epsilons. We have the target epsilon on the right, and the one that we predict, epsilon theta, given as input some xt. Okay? Which, in this case, we construct by starting from x0, jumping through the diffusion kernel to xt, using this transition, actually. We feed that as input to the neural network. It produces some guess about the noise, epsilon, which was used, and that's it. Okay? And if we have that, then, of course, we can reverse the reparameterization. Given a good guess of epsilon, we can recover this epsilon there, we can recover x0, and if we have that, we can recover the mean, and we know the distribution from which we should sample. Okay? So in summary, we arrive to these two algorithms made of 6 lines each, which is everything you need to know to almost to train and generate data from a diffusion model. So let's take it slowly. If you want to train, you start, so line 1 is actually so just a loop over your data. At step 2, you sample either one or several samples from your training set. So you sampled x0s. Then step 3, you sample an intermediate level of latent variables. So you sample some t, and you can do that simply uniformly from 1 to t. There are, of course, many other variations of these things, but they go beyond the scope of this lecture. Then you sample some epsilon noise from a standard normal distribution, which you use to construct xt given x0, and this is what you have. It's the first argument of the epsilon function. It's the construction of xt. And then you take a gradient step in the direction given by the squared error of the guess of the L2 norm between the noise epsilon that you've used and the one that you guess from the noisy piece of data. And then you repeat that until you have converged. Okay? Sampling, how do you generate data? You start from the last step at peak t, and then you go backward through time from t back to 1. So first you sample some pure Gaussian noise from a Gaussian distribution of 0 mean unit variance. And then you just follow your Gaussian transitions, these ones. Okay, where now we know this, we have trained a neural network through which we have parameterized this mean mu. The sigma t, the sigma square t's are also given from the alphas, so we can sample, and the way we would be doing that would be by just sampling noise z, and then doing Gaussian transitions, where we go from xt to xt minus 1 with a bit of noise. Okay, and then you follow all these sampling steps until you arrive at the beginning of the diffusion chain, and the very last sample you get corresponds to one realization of x0, which you can return. Also, if you paid attention there, you may have noticed that we just directly, there at least in this piece of code, they directly differentiate the squared norm, and they don't care about this. Okay, they don't reweight the gradients. It's because in practice, at least for images, it was found empirically that in terms of quality, perceptual quality, it was giving better results. If you want to do the proper training, in the sense of doing maximum likelihood estimation, you should add these scaling factors. Okay, what about the networks? Because so far I've talked a lot, but very little about the neural networks. Well, the neural networks, depending on the parameterization that we consider, either a neural network that takes as input a noisy image and then produce a clean version of it, or a noisy image and then would predict the noise. We may have to configure things slightly differently, but still it corresponds more or less to the problem of taking some piece of data as input and producing some other piece of data of the same dimension as output. Okay? And why? Because we have set the dimension of all the latents to be the same as the dimension of the data space. And so if we consider the case of an image, problem where that so we want to generate images. Let's take, for example, the interpretation of predicting the noise. We would take as input a noisy image, like this noisy cat, feed it through the architecture of the neural network, and we want the neural network to produce some output of the same dimension, which correspond to the noise added to that image, added to X0 to produce the inputs. And so we have an image-to-image problem. And so then we are just free to pick any architectures which could be appropriate for that. Every time we have an image-to-image problem, something like a UNet makes sense. And so this neural network that we have seen a few lectures ago, we can recycle it to actually generate data. There is still one little thing that we have to pay attention to, which is the fact that the neural network not only takes xt as input, but also the time step. So we have a very large image as input with a small scalar number next to it. If you just concatenate the image with the scalar, nothing will work very well. What we should try instead to do is to modulate, in a sense, the inner layers of the networks depending on the t that we are considering. And so what is done usually is to treat or to process the time step and to transform it using some kind of positional encoding, as we did with transformer, to go from one scalar to a vector of several numbers. And then we use these numbers to modulate the inside layers of the UNet. One thing, for example, that you can do is to use the positional encoding to modify the offset that you use inside nonlinear activation functions. Such that, so if, let's say you have a, I don't know, like a ReLU, like this, and xt and some intermediate quantity, let's say, would be maybe projected there in the negative regime of the ReLU, which produce nothing. So you would have ReLU of x plus some of x, usually. But you could say it's x plus some bias, some offset. And this offset could be a function, a neural network, of the time step. Not of x, of only the time step. Such that if you do that, it will basically shift either to the positive side of the ReLU or basically kill entirely the ReLU, depending on the current time step. In this way, you can have neural networks that can organize their activations depending on the current value of the time step. Does that make sense? More or less? Questions on this? Clear for everyone? It's a bit painful to derive all these things, but the reward is that we just have this at the end, so it's good. I could have given you directly this regression objective, but then you would ask me why. So now you know. Okay, so there is a third variation of diffusion model, which we call score-based generative models. I will not explain everything. But you should know this exists, and this is usually the formulation that we use these days in 2025. So it's there in the slides. If you are curious and want to study it, feel free. But you can just only study the two variations that we've derived if you want. Okay? But you should know they are not. There is something better, which is the third interpretation. And I will directly skip to the interpretation, which is based on the fact that you can, where is it? You can relate again x0 not to the noise, but to another quantity which is called the score. In this case, the score of the marginal distribution of the noisy data. And so the score is what is the gradient of the log density of a distribution. And in this case, if you follow the gradients, you will follow the direction which maximizes the density of the data. Okay? So there is a formula which exists, which we call 3D formulas, which relates some expected value to this quantity, and this is what allows us to rewrite x0 in this form. And then you do the same trick. You start from that template, you replace x0 with this other parameterization, and then everything simplifies, and you are left with this other regression problem, where now the goal of the neural network will not be to predict the clean image, will not be to predict the noise that we would have added to an image, but to predict directly this quantity, the score. Okay, so it should predict the direction that would increase the likelihood of the data xt if you were to follow that direction. Okay, this is what the score is pointing to. Okay, and so if you do that, then again everything is more or less the same as before. There is just one problem: is that that target we don't have either. Okay, it would be nice if we could directly learn it, but we don't have it. We don't have examples from which we can from which we can regress on. But we can use the diffusion kernel instead. We can use the conditional score, so the gradient of the log density of q of xt given x0. Okay, so the difference is the condition given x0. And because we will be minimizing this quantity in expectation over the x0s, it can be shown that the score that you will learn there will not correspond to this, but will correspond to the expected value over the x0, which is the target that really we want, which is the score of the marginal distribution of the noisy data. Okay? Okay, a few other things very quickly, but they are practically quite important. What if, okay, now they are no longer there, we want to solve task 2, 3, 4, 5, where we need to condition the sampling on something else. So far, we can only generate data as the data that we have from the training set, but we cannot do that conditionally on something else. You cannot generate images given a prompt. Nowhere I have talked about prompts or auxiliary inputs so far. So how can we do that? Well, the simplest, but also the least flexible, is to say, okay, if you want to sample conditionally from your distribution depending on some auxiliary input y, you could just say, well, you will insert this it's nowhere there. Oh, no, it's there. So when you generate following these transitions, and you want to do that conditionally, you could just say, well, I will add a new input, the y input there. Okay? And if you train on pairs of inputs and outputs of x and y's, then eventually it will work, and you will get, at the end of training, a generator which you can condition on these y values that you have also seen during training. However, if you look and consider the score interpretation of the diffusion, what we need for sampling is that score function, which also does not depend on y. Okay? But if we really wanted to sample from this, in terms of the score, the quantity that we would need is the score of the conditional distribution xt given y. Okay, that's our target. Okay, but so now we can use Bayes' rule and rewrite it as the sum of two scores. So you can just you take Bayes' rule and then you take the gradient of the log of that thing. Okay. And so the gradients are with respect to the xt, so you can re-express that as the sum of the score of the prior, p of xt, plus the score of the likelihood given noisy data, log of py given xt. And what is nice with this variation is that you can just pre-train once a diffusion model that would give you access to the prior, so the first term, And then only when you want to sample, without having to retrain anything, if you know the relationship that ties together the stuff that you are generating to the condition y, so if you know py given xt, then you can inject the gradient of the log density of that thing, and then follow instead this direction instead of the prior direction. So this is really something that we have never seen before. You can generate data conditionally on auxiliary inputs, even if you have not seen these inputs at training. And you will get the correct results. Okay, but of course that supposes that you know this term. It can be quite tricky. But for example, one simple, so if you want to understand how that could work, let's say you don't want to generate images on prompts, but at least over classes, like, I don't know, elephants, giraffes, lions, something like this. You have a class. And so what you need is this piece, py given xt, p of the class given an image. Meaning, in this case, you only need a classifier that goes from noisy image to class. If you have also a pre-trained classifier, which gives you access to a good prediction over the class, then you can combine your diffusion model with your classifier and obtain a conditional diffusion model of images given a class, among those that you can classify. And you can come up then later with another classifier about other classes. If your diffusion model is large enough, that's fine. Then you will only generate among those other classes. Okay, and then last but not least, what we call continuous time diffusion models. Okay, so one ugly bit in what we've derived is that we are stacking all these levels of latent variables. And okay, I've said arbitrarily we can pick up to 1,000 levels, and usually this is what was done in the literature. But what if we were stacking infinitely many of those those levels? Could we take the limit of considering a continuum of latent variables? The answer is yes, you can. You can have infinitely many intermediate levels, such that you consider continuous transitions between the levels. And the way you can understand that is by, and I will do it in this way, even though in the slide it's explained in the opposite direction. You can define, instead of defining a discrete diffusion process, where you have a discrete number of Gaussian transitions, you can define the continuous analog of that by specifying the diffusion process as a stochastic differential equation. Okay, where the stochastic differential equation could have this form, okay, where you specify the infinitesimal change over xt, and random infinitesimal change following this expression, where the first term is a guiding term which steers basically xt towards something, basically to 0, and then the other term is Brownian motion, so the equivalent of Gaussian noise in the continuous case, and in this case you also have, so this is the diffusion term which you scale depending on the variance that you want to achieve at the end. Okay? So you can just say, okay, this is something that I assume I preset my diffusion model to this SDE. Okay? And then you could just say, now I run this SDE. I solve this SDE. I start from an image, and then I follow the SDE. That will give me a trajectory, a continuous now trajectory, until I end the equation. And so you could go, for example, continuously from t equals 0 to 1, and then you have all the intermediate values in between, continuously. And you could also define these beta coefficients, so they are the equivalents of the alphas, such that at the end, once you have run this SDE from 1 to t, what you obtain are samples for which there is no signal anymore. Okay, exactly as we did in the case of discrete Gaussian transitions. So in the slides, what I say is that actually the Gaussian transitions that we consider, if we re-express them in this way, so we say that the alpha t are reparameterized as 1 beta t. I'm just flipping the convention, because that's what they do in the literature, even if it's a bit confusing. And then I re-express the beta t as a continuous function of t. Okay, so I redefine beta t as a function of t times some delta t. Okay, there everything is still discrete, but if I say then that delta t goes to 0, so now I will be considering the limit of this discrete process, then we arrive to this, and then if you Taylor approximate the first term, you get this, and this one, this term, this equation that goes from xt minus 1 to xt correspond to the discretization, or specifically of the Euler-Murayama discretization of a stochastic differential equation. So basically what I'm saying is that the thing that we've derived, you can see that as a special case of that SDE. Okay, where we've assumed some specific scheme for the discretization of that equation. Okay, and the nice thing about this framework is that there is a very old result which says that if you have an SDE that runs forwards, there is a direct form for the reverse time SDE, which is given by this equation, where everything is known, so the betas are the same as in the forward SDE, but they are used a bit differently to produce other scaling factors. And so the reverse time SDE is itself something that you can follow, okay? And so you can now start from pure Gaussian noise and then run this reverse time SDE to produce, at the end of the equation, a sample as if it was drawn from x0. The distribution of x0. And you see that, okay, that's fine, that's nice, but you need this term. But that's the score. That's the same quantity as the third interpretation. So provided that you can approximate the score, you can plug in your approximation in this reverse time SDE and then generate data by following that equation. And you would do so, you'd learn the score by using the same denoising score matching objective as the one from the third interpretation, in which we would minimize in the sense of the squared error the difference, the norm, sorry, of the difference of the prediction of the score and this quantity, which is given, which we know also from the diffusion kernel. Okay. Okay, and then if we want to make the further connections, so I've told you that now with this interpretation we can just follow the reverse SDE, but actually what we care about are just the final samples, right? The fact that it's an SDE itself, it's not that interesting, and that can be a bit difficult actually if you want to be efficient. But there is another result which says that if we just look at the marginal densities of this process, so the P of xt's, then there exists a corresponding ODE, so an ordinary differential equation, non-stochastic, which shares the same marginals. And again, this is something that we know analytically. So for any diffusion process, there exists a corresponding deterministic process, okay, where everything is now non-random, given by this equation. And what is nice is that the marginals of this will be the same as the marginals that we would have obtained by following the reverse time SDE. Okay, so that means when you solve this equation, and if you do that just with a simple for loop, with a Euler discretization, you would be making these small transitions. Okay? And that means now the neural network that we have is a neural ODE, just a differential equation where some part is given by a neural network. And we have seen from 2 lectures ago that in this case, we obtain what we call a continuous time normalizing flow. Okay, so this is just to make the connection between different things that we have seen. You can basically tie together or make a stretch from a VAE to a normalizing flow through the diffusion, then the continuous diffusion, the continuous normalizing flow, and then the normalizing flow. And if we had time for a final lecture, actually you can make the connection with other things, which is also state-of-the-art, which we call flow matching models, which are generalizations of everything that I've mentioned here. Okay, one last thing. So everything that I've told you so far is defined at the level directly of the data space, for example, at the pixel space, and directly we do the diffusion in the pixel space. If we have very high dimensional objects, then learning this network at the level of the pixels can be quite heavy. So one trick which we use often now these days is to go through an intermediate space, a latent space, and we do that by using an autoencoder. Not a variational autoencoder, but you could also use a variational autoencoder, but just a regular autoencoder, which gives us a mapping between data space and some compression of that space. And then, once we've learned this autoencoder, we learn a diffusion model in that compressed space. And this is how then you can scale to high-resolution images, how you can scale to videos, or also how you can scale to these weather systems I've mentioned at the beginning. Questions? And this is one of those videos generated by these models. Okay. Okay. I have a few more slides, just closing remarks, and then I will free you to dinner. Okay, let me close that. Okay, so this is just a few slides to summarize the course. So we have covered quite a few things, I know. So we started with the fundamentals and like everything you should remember about machine learning, the ways to train models, the protocol you should follow, everything remains important when you will train neural networks, so don't forget about that. Then after that, we started building our first neural networks with multi-layer perceptrons, starting from the logistic regression unit, and then composing these units in parallel to obtain layers, and then layers to obtain networks, and so on. Then we started wondering how can we actually train these neural networks. So we could do gradient descent, stochastic gradient descent, but the first thing, if we wanted to do that, we would need access to gradients. So how can we obtain these gradients without having to write them by hand? So we covered automatic differentiation, which are algorithms that you can use for that purpose. And then once we have these gradients, then we can plug them into optimization algorithms, and we have seen many of them in the fourth lecture, including, among the most popular, Adam and others. Then we covered specific architectures, or I would say more advanced architectures, even if some of them are quite old already. For images, we talked about convolutional neural networks, and then we extended that to other tasks than just classifying images. We've talked about segmentation, object detection, and a few others. Then we moved on to architectures a bit further than tabular data or image-like data. We talked about attention mechanisms and the transformer architectures, which we have implemented to obtain the GPT model. And then we have extended that or generalized that with graph neural networks. And then finally, the last 3 lectures were dedicated to uncertainty and generative models. In lecture 10, we covered neural network that you can use to model allegoric uncertainty directly through the output layer of the network. We've covered normalizing flows. We've covered Bayesian deep learning if you care about the uncertainty that you have, not about the output, but about the model, the neural network itself. Then we moved on to generative models per se, even though normalizing flows, strictly speaking, are also generative models. We've talked about variational autoencoders that we've derived from autoencoders combined with variational inference. And finally, today, we generalize that further to diffusion models. Okay, so my mission, if you remember, was as follows. I've told you by the end of this course, you will have a strong and comprehensive understanding of deep learning. To be honest, I've covered a lot, but there is still a lot to be covered if we wanted. But you should really have more than the fundamentals. You should be quite comfortable now in just picking and learning about new stuff if you want that we've not covered in the course. I've told you that you will learn how to design deep neural networks for various inference tasks and how to train them. That's something we've done indeed. And that the applications of these models are quite broad. So you can use them, of course, just to do AI, but they have many practical applications directly in engineering and in science. Okay, my main message would be this slide. And this is really the philosophy that I have myself about deep learning. Some may tell you that deep learning is just training neural networks. It's a shortcut. It's that indeed, but it's much more than that. To me, it's really a methodology. It's to take Lego bricks, if you want, and then to compose them into functional blocks, and then to iterate further, to take these functional blocks, and then to compose them again into bigger architectures. Exactly as when you design a big piece of software, you do that by defining basic components, or it depends. You may start from the bottom and then combine everything, or you have a big design in your mind and then you instantiate everything from top to bottom. You can have really the same philosophy when it comes to deep learning and designing architectures. And so this is something that you should really realize. And so meaning, certainly, one thing which you can do now is to really build and create architectures that are tailored for the problems that you want to solve. Okay, it's not deep learning is not just about classifying images. That would be so boring. You can do so much more with that. And so basically what you are basically creating now are programs, in a sense, and programs that you can train. And this is how it's different from regular programming. You write a meta program in the form of the architecture, and then you train this program directly on data to actually solve the task that you could not express yourself directly in a regular programming language. Okay? So this is very powerful. The bricks are quite simple, but their composition basically can really be very complicated and solve important problems. And so the message to me is really think like architects, if you want, and try to build cathedrals of neural networks. Okay, a few disclaimers still, because these days we are hearing a lot about AIs and the dangers of AI and why you should not do AI. So 3 more slides. I would say the good first. So deep learning to me has become a powerful tool for solving many important problems in various fields, as I said already, and not just to do what we could do already before. That's fine, but that's not very deep either. You can use deep learning and AI more generally to solve problems we couldn't solve before. What is new and nice is that the human-computer interface is rapidly evolving. And so these days, if you ask anyone, even those that have not followed AI or discourse about AI, they know about it and they can use it. Okay, why? Because there is a change of the interface. Now you just talk to this system, you write to this system, and they answer. What's different from your perspective now is that now you should also be able to build them if you want it. But this means that, okay, more and more people will be using about AI and realizing about the strengths and also the many shortcomings of these systems. The good is that progress is going very fast. I mean, good and bad, depending on your perspective, but we are improving things. The lectures I was giving a few years ago are quite different from what I'm giving now, a few years later. And that's something also you should expect. What we've covered and generally what we cover in the courses about AI, certainly in 5 or 10 years will be quite obsolete. I don't know if that's good or bad, but we are making progress, we are improving things. The bad, deep neural networks, even though they are quite powerful, they are difficult to interpret and explain. And that's an obstacle that certainly you will face every time you build a neural network to do something which is even only a tiny bit sensitive. You want, and the outcome of the neural network should be used by someone, a human, then certainly you will want to interpret and understand why the predictions are this and that. But unfortunately, that's something which is still very difficult with neural networks. You get a result, which is good most of the time, but you can't explain. I mean, you can explain how it was produced mathematically, but that's not very satisfactory. You don't get a human explanation about why the prediction is like this. What you should also realize, but I suppose you do realize that, is that the system, they can make mistakes, they will make mistakes, they are not perfect, they are at most only as good as the data, and the data already is not perfect. But don't forget about that, neural networks at the out are basically byproducts of the data sets. Okay? And when it comes to conversational agents, what is even more worrying is that they will make mistakes, but they may appear very confident about stuff they say, even though it's wrong, because they don't know that they don't know. So don't be fooled, I would say, by the confidence of this system. They don't know if they know, and they don't know if they don't know. That's quite different from a human, which either has gathered expertise and he knows that he knows, but if I ask you, I don't know, how to treat someone who is sick, you know that you don't know and you will not say something silly. This system, they don't know. And finally, about the bad, is that these models, they've become very large and they require significant computational resources, which means that the environmental impact of the system is getting bigger and bigger as more and more people are using them. Then we are just multiplying all these consequences by the number of users. And that's also something that you should be worried. And finally, the ugly. Deep neural networks, they can be biased. So not only they can be wrong, but they may have opinions, even though they don't realize that. They may have opinions, which are just the reflect of what is inside the data set. So these bias, they will be perpetuated, and they may even be amplified. So if you follow the social networks, that's something that you see almost every day now. With the system, with ChatGPT, with Grok and others, they are heavily biased by the political positions of their companies. Malicious use of AI is becoming more and more common. So, of course, you can do great things, you can discover new drugs, but you can also repurpose the same methodology to produce deepfakes, to produce bots, to manipulate massively the opinion of people on social media. So, yeah, so that's a worry. And finally, the last point I wanted to make is that there is a growing dependency on AI in almost all areas of society. I suppose that yourself, you using more and more these tools, and we just think for 2 seconds, if we remove them, if OpenAI turns down, what do you do? It used to be not a problem. Students could think by themselves a few years ago, but if you depend too much on that, you should realize that you are basically delegating a bit of your own thought process to this system, and that is a danger. Okay, now what? The exam, of course. Okay, so how will that work? So I've sent you the questions I will ask during the exam, so you can just prepare them. If you prepare them yourself, certainly you will have studied well the course. If you study the summary of someone else, okay, either you have a good memory, but may not be the best strategy. The fact that you do yourself your summary is your study. If you use someone else's summary, it's not the same output. And I'm saying that because from year to year, I'm just usually reusing the same questions, and I see errors. I don't know where they come from. They are not in my slides, but they are perpetuated by more than one student. So pay attention to this. So you will have questions on the fundamentals and on advanced topics. But when I'm saying that, it does not mean that you will be asked 2 questions of the list. Okay, you will be asked one of those, but inside each of them, I will probe the 2 parts. I will probe the fundamentals, and I will probe the advanced topics. Okay? So you will have 1 or more blackboards to prepare, 30 minutes or more if you need, and then we'll have a discussion about what you have presented. Okay? I like to ask questions to make sure that you understand everything that you've put on the blackboard. So if you're not sure, don't put something that you know you will get asked question on. And also, and that may be a bit puzzling for some of you, I will go as far as also asking questions about how you would implement this on an actual computer. Also to test whether your knowledge goes beyond theoretical understanding to practical understanding. Okay, and finally, one of the teaching assistants will also ask a few questions on your project, okay, which are still due for next week, if I'm not mistaken. And so what we'll do is that usually we take the code that you've submitted and ask a few questions directly about the code. Okay, if you did the project, usually that's super easy, but if you have not and just added your name to the report, usually that's going not so well. If you can't answer our basic questions, you will have a penalty of -5 to the project. And it's things that are quite easy, like, can you show me the loss function that you have used in the code? You would be surprised by how many students can't find it. Or why did you choose this architecture? And basic things that if you did the project from the beginning are super easy to answer. So don't be stressed about this part if you did the project well. Okay, so if you pass the exam, you will pass the course, and if you are not yet bored or disgusted by the topic, there are many more courses that you can follow about AI and deep learning in general in the program. So supposedly you should have already followed Intro to AI, Intro to Machine Learning, and now Deep Learning. If you want to continue further, you should know that there are more courses available. Advanced Machine Learning, which is given by myself, Per Gerst, and Louis Winkel, where it's organized as a journal club about scientific papers from the field. Reinforcement Learning, given by Damien. Introduction to Intelligent Robotics, given by Pierre Sacré. Computer Vision by Mark van Roggenbroek and Anthony Chiopa. You should know that there will be a new course, Computer Vision 2, or Computer Vision Understanding. It will be created and available next year. the next academic year, and also a new course which was created 2 years ago, Machine Learning System Design, which is a course about how to deploy machine learning model on cloud platforms and all these things. If some of you are already considering topics for master thesis, feel free to ask me if you want to do something about deep learning, about what we do in our group, or if you are looking for a master thesis in a company but related to deep learning, you can also ask me if you want me to be the academic supervisor, because you will need one, or ask someone else, but I'm just saying I can also do that and support that. And if some of you are also maybe considering to continue after your master study by a PhD, we have also quite a few open positions in the lab. Questions? Comments? Okay, then that's it. Thank you. See you in June.